everyone, welcome back to my YouTube channel. I am Jayashree, currently pursuing second year B in the Department of Computer Science and Engineering at Sri Venkateshwara College of Engineering. Today I will be presenting the topic of data structures and its limitations. Throughout this presentation, we will explore introduction to data structures, arrays and their limitations, linked lists and performance concerns, stacks and queues, trees and scalability issues, graphs and memory constraints, conclusion and recommendations. Okay, let's begin the session. Data structures and their limitations. Data structures are the fundamental building blocks of computer programming designed to efficiently store and manipulate information. However, each data structures come with its own set of limitations and trade-offs that developers must consider when designing their applications. Understanding these limitations is crucial for choosing the right data structure and optimizing system performance. Introduction to data structures. What are data structures? Data structures are the way in which data is organized, stored, and manipulated within a computer program. They provide a structured approach to managing information and enable efficient retrieval, insertion, and deletion of a data. Common data structures. The most widely used data structures include arrays, linked lists, stacks, queues, trees, and hash tables. Each of these structures has its own unique characteristics and is suited for different types of problems and applications. Importance of data structures. Choosing the right data structures can greatly impact the performance and efficiency of an application. Understanding the strength and weakness of each data structure is crucial for designing effective algorithms and optimizing system resource. Arrays and their limitations. Advantages of arrays. Arrays are simple and widely used data structure that provide constant time access to elements by index. They're efficient for storing and retrieving data in a contiguous block of memory. Limitation of array. Array have fixed size, which means they can only store a predetermined number of elements. Inserting or deleting elements in the middle of an array can be inefficient as it requires shifting all subsequent elements. Addressing array limitations. Overcome the limitations of array, developers often use dynamic data structures like linked list or resizable arrays. Example, arrays list in Java to provide more flexibility and scalability. Linked list and performance concern. Linked lists are a dynamic data structure where each element, called node, contains a reference to the next node in the list. This allows for efficient insertion and deletion of element, as well as variable-sized storage. Performance consideration. While linked lists offer flexibility, they can be less efficient than arrays for certain operations. Accessing an element by index requires traversing the list, which can be slower than direct access in array. Optimizing linked list. To address the performance concern of linked lists, developers may use specialized variations like doubly linked list or skip list, which provide additional functionality and improved efficiency for specific use cases. Stacks and queues. Stacks. Stacks are a last in first out data structure where elements are added and removed from the top of the stack. Stacks are useful for managing functions, calls, frames, undo or redo operations, and parsing expression. Queues. Queues are first in, first out data structure where elements are added to the end of the queue and removal from the front. Queues are commonly used for task scheduling, event handling, and breadth first search algorithm. Trees and scalability issues. Trees data structures. Trees are a hierarchical data structure that organize data in a branching structure with a root node and child node. Trees are used for efficient searching, sorting, and traversal operations, and here are their foundation for many advanced data structures like binary search trees and heaps. Scalability concerns. As the size of a tree grows, the depth of the tree and the number of nodes can increase significantly, leading to potential performance issues. Balancing the tree, such as through technique like AVL trees or red-black trees, can help maintain efficient lookups and insertion times. Optimizing tree performance, developers can employ various optimization strategies for trees, such as using specialized tree variants, implementing caching mechanism, or leveraging parallel processing to handle large-scale data sets and maintain high performance. Graphs and memory constraints. Graphs are a data structure that represent a set of objects called vertices or nodes, and the relationship between them called edges. Graphs are used for modeling complex interconnected systems and enable efficient traversal and analysis for these relationships. Memory consideration. Graphs can require a significant amount of memory, especially for large, dense graphs. Developers must carefully consider the memory footprint of their graph data structures and optimize them of fit within available system resources. Using techniques like adjacency list or compressed space row representations. Balancing performance and memory. Striking the right balance between performance and memory usage is crucial when working with graphs data structures. Developers may need to make trade-offs such as using a more memory efficient representation at the cost of slight slower traversal times. Conclusion and recommendations. We already knew that data structures are the fundamental building blocks of computer programming, and understanding their strength, weakness, and limitation is essential for designing efficient and scalable systems. By carefully selecting the appropriate data structure and optimizing its implementation, developers can create high performance applications. Some key recommendations for working with data structure includes understand the characteristics and trade-offs of each data structure. Choose the right data structure based on the specific requirements of the application. Optimize the data structure performance through techniques like caching, parallelization, and balancing. Analyze the algorithmic complexity of your code using Big O notations. Stay up to date with the latest advancements and best practices in data structure design and implementation. Thank you all for your support. Don't forget to like, share, comment, and subscribe to my YouTube channel.